What are we talking about? We're talking about transient analysis. So what happens to a circuit that has energy storing components like capacitors and inductors after a major change happens? A switch opens or closes, the value of a source changes, pretty much anything that you can think of that would change the state. And so we look at that short period of time between the perturbance and when the transient settles and when things go back to their steady state. And so what we see is that this type of analysis draws upon tons of stuff from your ENG212. And actually, hopefully this is nice in one way that it really illustrates how the stuff from advanced engineering math is applicable to quote-unquote real engineering problems. And so we're representing the system as a first-order differential equation, and we need to solve that in order to figure out what the transient is. We are going to talk about second-order differential equations, and that is going to address circuits that have two energy storage elements. So here we're talking about RC or RL circuits, and then when we get to the second-order differential equation, we'll be diving into RLC or circuits that have all three of those components. So last time, specifically, where we had stopped was at the end of a process where we were trying to solve an equation that was in the form shown here, this form. And what we saw was there's a process that requires us to split the solution into the complementary and particular solutions, right? As shown here. And by doing that, and using some combination of algebra and calculus, we're able to solve and end up with this solution here. So the solution has a steady state component, which is denoted by the particular solution, and then a transient solution, which is denoted by the complementary. And so that's a constant plus a constant times e to the negative at. So that's just a form, right? That's not a solution because we don't know what a is. We don't know what K1 and K2 are. So we still need to talk about how to solve it completely. And we're going to do an example today where we're actually given a physical circuit. We're going to represent it as a first-order differential equation, and we're going to go through all the steps specifically in coming up with the numbers that we need to get the full solution. Okay, now before we move on though, there's one thing that we need to talk about with regard to this equation here. So K2 e to the negative at. Another way of writing this, we could take the a and so instead of negative something times t, we could do negative t divided by 1 over a, right? So 1 over a is a value that we're going to refer to as the time constant, which is equal to tau. And so we've talked a little bit about practically what that means. Tau represents the length of time that it's going to require, that it's going to take for the transient to settle. And this makes sense when you look at where it is in the math. Because, right, if tau is small, then that means that this value is going to get very negative very quickly, which means that e to the is going to get small very quickly, which means that the transient will go away. That is at the beginning, and the value is K1 plus K2, so that's the reason why it's the top green line. After a long period of time, this will drop to 0, the K2 will go away, and so at the end of the transient, it will be equal to K1. Right? So we go from K1 plus K2, and we go down to K1. And so let me write a note here to try to clarify this. It's going to be interesting how I'm going to edit the video to get rid of that part where I'm like, there's going to be a skip. I was like, what did he do for 30 seconds right there? All right, so let's write a little note here. So at this point, and really the part that was tripping me up was e to the negative t over tau will be equal to e to the 0 over tau, which will be equal to 1. Okay, that's what's going on right there. Down here, we have e essentially to the negative, I'm going to say large value over tau, which is going to be equal to 0. Okay, so that's the difference between those two dotted lines. Okay, so now that we're clear on where the transient starts and where the transient ends, we can talk about what the time constant means. So the time constant is right here. This is t0, this is t0 plus tau. And so the intersection is the value of the solution at tau. So what happens? Dropping from here to here is 100% of the transient completed, right? We're going from K1 plus K2 down to K1. 50% of the transient drop would be right about here. And so what is this line? This is labeled, it's 63.2% drop. So what happens is that the tau indicates the point at which we've dropped 63.2% of the total drop that's going to be associated with the transient. What's left is 36.8%. So if you look at the value of this line, it's going to be K1 plus 36.8% of K2, which happens to be the difference between those. So when we say that the time constant represents how long it takes for the transient to settle, that's maybe a better way to say that is it's reflective of how long it takes the transient to settle. Larger time constant means the transient will be longer. I don't know if eyeballing this, you would consider this point to qualify as the transient already having settled. But in the end, the transient is never, at least mathematically, is never going to completely settle, right? The exponential is going to reach an asymptote. So we have to set a threshold regardless. That could be 1 time constant, 2 time constants, 3 time constants. But the time constant gives us a numerical value that we can define. We know exactly what it means physically. And we can use 1, 2, 3 multiples of it. And that can be our threshold for considering when it has settled. So the takeaway from this graph is that time constant is not just a number. Okay, time constant is something that you can observe physically. So I don't know if you did this in ENG214, but in ENG214 you should be able, there's one lab that should have required you to observe a transient. You can calculate the time constant and then go on the scope and physically look and see that within the amount of time that you calculated, it should have dropped about 60% or so. Okay. So the next section is going to dive into the electrical circuits end of this problem. So far we've just been talking about math, okay? How do we relate this back to first order transient circuits, R's and L's and C's? So we're still going to use this form, and that's the reason why the previous section was important, because we needed to talk about how to solve the math. But now we're going to analyze an actual circuit and arrive at a solution in this form, and we're going to use something called the state variable approach. Now the state variable approach is not really anything that complex. All it's saying is that when we have problems that are involving a capacitor, we are going to choose the voltage across that capacitor as our state variable, meaning that's the variable that we're going to focus on. It makes sense. We're trying to solve for that value. And then for circuits that have an inductor, the current through the inductor is going to be our state variable, and that's going to be what we're focusing on. And what that means is then when we write the equations, we need to write a form that includes the appropriate variable. So we write the equation for the voltage across the capacitor and or the current through an inductor when we use the state variable approach. This is important because VC and IL cannot change instantly. I would say they're also important because they're going to be the basis for the first order differential, right? And these are going to be our state variables. So I kind of already said that there. All right. So now let's jump into an actual... yep, sure. So while some of you write this down, Chapter 7 homework is up on the website. I am not going to be collecting either Chapter 6 or Chapter 7 homework, and obviously at this point we're not going to have a Chapter 6 or Chapter 7 quiz. My recommendation is this. Chapter 7 is difficult, okay, as you can see. Chapter 6 is not that difficult. So if you have a pretty good understanding of how inductors and how capacitors work, I don't think there's a need to spend a ton of time on that material. And I would shift whatever homework time or whatever studying time you're already looking forward to the exam now, I would emphasize Chapter 7 a little bit more. And again, during the last week of classes and during the review session, I'll give some more guidance on exactly how things are going to be divvied up. Okay, so solving for the transient response of this circuit. So we have this, an RC circuit connected to a DC source, and there's a switch that closes at time equals 0. So this is the form of problem that you're going to see in Chapter 7 a lot. We have one or two energy storage elements. You have some sort of a switch that's going to be thrown. What's the response? Okay, so the first thing that we need to do is we need to figure out what is the steady state solution that precedes the perturbation. Okay, if it's not given to us, we need to figure that out. And the reason why that's important is because we will need the initial condition of the voltage across the capacitor in order to solve all the parts that we need to solve. This one is easy in that regard because if we're trying to find the initial condition of the voltage across the capacitor before the switch closes, it's just going to be 0, right? I mean, I wrote out an equation based on KVL for it. VC is equal to VS minus VR. But ultimately, when the switch is open, there's no current flowing through the resistor, which means that there's no voltage drop across it, which means that VC equals VS. VC equals 0. There's no voltage being... No, this is... Sometimes when you say things, they... Sometimes when you say things, they become obvious. When you're writing them, they are not so obvious. Okay, so the initial condition of the cap is going to be 0, right? There's no source connected to the cap before the switch is closed. So that's easy. All right. So now moving on. Step 2. We need to declare that VC is our state variable, right? This has a capacitor. And we're going to generate an expression that defines it with respect to the rest of the system. So more or less, for the problems that involve the capacitors, we'll be using KCL. Because that'll give us an expression in terms of IC, and then IC is a function of dVC dt. So let's Actually, in this case, we use KVL, so this breaks the rule that I just set. But maybe I should go ahead and not state a rule. So essentially, what you need to do regardless is you need to find an expression, whether it's KCL or KVL or whatever, that puts the system in terms of VC. And so what we used here was KVL. The voltage across the capacitor is equal to Vs minus IC times R. Okay? And so then now we can substitute in for IC with C dVc dt. And actually, it makes sense that we would have to use KVL for this because it's a single loop circuit. As we've seen in the past, applying KCL to a single loop circuit doesn't yield a very interesting result because, right, all of the currents in the loop are going to be the same. In the same way that applying KVL to a single node pair, again, doesn't yield a very interesting result. Okay, so we take this circuit here. We generate an expression using KVL. We substitute for Ohm's Law, IR, and then we substitute for the current using C dV dt. And so that leads us to this form here. Okay, now the next step is that we want to, yeah, sure. So the next step is that we don't want to have to solve this differential equation from scratch again. Okay? If we can put this into the form of the first order differential equation that we already solved, then we can go ahead and use that same solution. I mean, we obviously will have to solve for a couple of the values, but that will be much easier. So we want to put this expression into the form of dx dt plus ax equals f of t. Right? This is our general form. X is going to be Vc of t. And the reason for that, again, is because x is our state variable. We said in the state variable approach that the voltage across the capacitor was going to be that state variable. All right. Now, there's a couple of differences between this form and this form. One specifically is that our derivative has a coefficient. And actually it has two coefficients, R and C. So anyway, all we have to do really is divide by RC. If we take this divide by RC, we do that to all the different elements, then what we'll end up with is a form that looks like this. dVc dt plus 1 over RC Vc equals Vs over RC. So no coefficient for the derivative. That's good. 1 over RC will take the place of the lowercase a coefficient. Vc of t equals Vs over RC, which is going to be our externally applied force. This problem, the way it's stated, supports the assumption that we made when we solved the differential equation last class, and that assumption was that the f of t is going to be a constant. So in ENG212, you talk about how to solve these types of problems. I believe these types of problems where f of t is actually a time-varying function, but we're not going to dive into that level of difficulty. Okay, so you know how to solve that problem. We're just not going to go over it here. So now that we have the form that we want, let's combine the solution that we came up with previously with the differential equation above. And so the solution we came up with previously was this guy, right? The state will be equal to K1 plus K2 e to the negative t over tau. So we know the form, but the the thing that we have to do still is we need to figure out what is the K1, what is the K2, and what is the tau. So in order to do that, we're going to take the original problem and we're going to take our solution and we are going to substitute it in. Okay? And when we do that substitution, it's going to give us some opportunities to solve for K1, K2, and tau. So let's go ahead and do this. So 1 and 2 are already equations that we've seen, our original problem, our prior solution, and so now we substitute 2 into 1. And I'm going to do the two solutions separately. So let's first substitute K1 into the differential equation. That's here, and then we'll substitute in the other part. So what's the derivative of K1? 0. That goes away. Then we're going to put in A times K1. So these two terms are associated with the particular solution. Next, let's take the derivative of K2 e to the negative t over tau. That's this part. And what we end up with is negative K2 over tau e to the negative t over tau. Right? The derivative of e to the alpha x is going to be equal to alpha e to the alpha x. So we're pulling out the coefficient to the t. And the last piece that we haven't dealt with is we'll simply have A times the complementary solution K2 e to the negative t over tau equals f of t, which we know what that is. So this right here represents the combination of 2 and 1. So what we end up with is one time varying term and, well, two time varying terms and one constant term. And then A and f of t, we can fill those in with the constant that we already have figured out. Right up here, we determine what the value of A was. It's 1 over RC. And we determine what the value of f of t was. It's Vs over RC. Okay. So we have this not very simple looking differential, well, it's no longer differential, time varying equation. Okay. So how the heck are we supposed to solve for K1, K2, or tau from this? It doesn't look like it's particularly helpful. But there are some things that we can pull apart. So first things first, we can imagine that there's another term over here, 0 times e to the negative t over tau. Okay? And so we know that this plus this has got to give us 0. Right? Because those are the terms that are associated with the e to the negative t over tau. This plus this should sum to 0 because there's no e to the negative t over tau on the right-hand side. So they gotta cancel out. Or else we would have an e to the negative t over tau on the right-hand side. Then that also tells us that this has got to be equal to this, because the constant term on the left-hand side has got to be equal to the constant term on the right-hand side. So although it's not terribly obvious at the very beginning, there is a good matchup here between these terms. Right, where we know that their coefficients are supposed to sum together. Okay, so so far we have two different equations that we can work with. What's in the green and what's in the yellow. Actually, I'm going to get rid of the highlights because they never show up on the video. So, the constant terms have got to zero out. K1 over RC has got to be equal to VS over RC, and so we know that K1 is equal to VS. So that's one of three values done. We got K1. We still need K2 and we need tau.
Can I help a little bit?
Yeah, sure. So this first equation is going to be looking at those two together.
Is that 0 then?
It is 0. Because this term doesn't really, quote unquote, exist. There is no exponential term on the right-hand side. Okay, now the second equation looks at this and this and this. And so what you'll see is negative K2 over tau plus K2 over RC equals 0. This is the coefficient of the one exponential. This is the coefficient of the other exponential. And then we have, right, we have no exponential on the right-hand side. Okay, and so these coefficients must equal 0. The K2s will go away. And so what we'll be left with is the fact that tau must be equal to RC. Okay. So we used up that equation. There's no way we can split this up right here. We can't split this up into any more parts. Unfortunately, we've only gotten 2 of the 3 values that we need. So what is a method that we could use to get the third value? Is there any information that we have that we haven't used yet? We did something at the beginning. We determined what the initial condition was for the cap, right? And we haven't used that piece of information yet. So we still don't know the value of K2, but we can determine it by the initial condition across the capacitor. So we know that the solution, which is K1 plus K2 e to the negative, etc., should be equal to V0 when this is equal to 0, right? All we're saying is, yeah, sure. All we're saying is that when you plug in T equals T0, or T equals 0, same thing, that it should be equal to the voltage at that time, which we figured out what that value was. It was a 0 in the very beginning. And now, because we have 2 of the 3 values that are known, we know what K1 is, we know what tau is, we have one equation and we have one unknown. And so what we're left with, we'll plug in T equals 0, which will make this portion here, it'll make it turn into a 1, right? Because that'll be e to the 0. And what that will leave us with is that K2 is equal to VO, which is, this is what we're calling the initial condition. It'll be equal to VO minus VS. And so in this case, our value of VO was 0, so it would be equal to minus VS. And so when we write out the full solution in the final form, it looks like this. VC, and that's not T0, it should be just T, okay, is equal to K1 plus K2 e to the negative t over tau. But we figured out what all the values were. So then K1 is Vs, K2 is V out. This is the initial condition. V out minus Vs. So I'm calling it V out. If it's initial condition, it should be V naught. I guess it's a 0, not an O. But so V naught minus Vs, e to the negative t over Rc. And we have our solution. So what this example does is it combines the work that we did previously, the mathematical work previously, and it shows how we can take all those principles and essentially the form of the solution that we already got and use it to solve for the transient response of the circuit without having to do the calculus part again, right? We're just going to be applying that same form. So, can a similar solution be found for an RL circuit? Yes. Yeah, sure, no problem. So can a similar solution be found for an RL circuit? Most definitely. If you look in the textbook, they go through a whole similar derivation for this circuit. And so I'm not going to go through it because there's a lot of parallels. I think enough that you should be able to take a look at it on your own. You're going to use the state variable approach. IL is going to be our state variable. We're going to find the initial condition. What is the initial current through the inductor, which in this case will be 0. We'll write out an expression that puts the system in terms of IL. Again, it's going to be a KVL-based expression. Then we're going to try to put that differential equation into the form of dx dt plus ax equals f of t. Then we're going to take our solution and plug it into the differential equation. We're going to solve for k1 and tau using the differential equation. We'll be left with k2. Again, all the exact same things. The way that I describe it, I don't even have to change the language when discussing the capacitor problem versus the inductor problem. Okay, so now let's take a look at another example. So this one is a little bit different, right? This one has 2 resistors as opposed to 1. And it's a little bit different. I forgot a line here. The circuit is not dead in switch number 1 for t is less than 0. Anyway, let's jump right in. More complex example. We want to solve for the transient response here of V of t as well as I of t. So first step, calculate the steady state value of V of t when t is equal to 0 minus. So I haven't used this notation yet right here. What does this mean, t equals 0 minus? Essentially, if you imagine that this is t equals 0, and you have your transient response, right? This is t equals 0. As close as we can get to t equals 0, but just barely on the other side of it, that we call 0 plus, and on the other side we call 0 minus. So t equals 0 minus is essentially saying it's t equals 0, but on the steady state side, right before the disturbance happens. T0 plus is what happens is the first instant of the transient response. So when we say find the steady state value at t equals 0 minus, that means what is the steady state response? What is the steady state value right before the perturbation happens? Okay. So how are we going to do that? we're going to draw out the circuit, including the components, how they would be represented for DC steady state analysis. How is a capacitor represented for DC steady state? It's shown, and we've talked about it. I know it's Thanksgiving week. Everyone's ready to get out of here, huh? It's okay. I'm also looking forward to the break. All right, so it's represented as an open circuit. So you can see we replace this capacitor with an open circuit. The switch position is 1, meaning that this additional little mini branch here doesn't need to be represented. So we have a DC source, and we have 2 resistors, and we have the capacitor, which doesn't play any role. So the value of V at t equals 0 minus is going to be represented simply by a voltage divider, right? This is a nice voltage divider. It's equal to 12 times R2 over R1 plus R2, 3K plus 6K. And that gives us a value of 4 volts. So the initial value across the capacitor is equal to 4 volts. Next step. So this example is going to be step by step a retreading of what we just did, just with the circuit being a little bit more complicated. Okay, so you could essentially take all the step names. I probably worded them a little bit differently, but you could use that same wording and it would still apply to this example. So we're going to redraw the circuit to reflect the position for the switch during the transient period. So what does it look like at t equals 0 plus? So when the switch is in position 1, the source that was over here is no longer going to be represented. And now we have this additional pathway, which is going to close off the circuit. Everything else stays the same. VT is still the same. IT is still the same. The resistor and capacitor values are still the same. Only thing I did was I drew in a couple extra labels. I'm going to call this current I1, and I'm going to call this current right here IC. Okay, so yeah, 1 second. Okay. Sorry. I'll be posting these notes online as well, and the video and everything. So, I mean, get down as much as you can, but if you miss an operator here or there, you'll have a chance to take a look again. Okay, so now we have a single node pair circuit. The voltage across all 3 elements is VT. And so it's going to make sense for us to use KCL to analyze this circuit. We're using the state variable approach, which means, again, we want to focus on the variable V of t, which is the same as Vc of t. All right, so KCL, I1 plus IC plus IT equals 0. All 3 of the currents that I have drawn on the circuit are heading out of the node, and so we can sum them together and they should equal 0. Then I'm going to substitute Ohm's Law. So I1 t is going to be equal to Vt divided by R1. Substitute the VI relationship for the capacitor. IC equals C dV dt. and then Ohm's law again, Vt over R2. Right? That's all we did. Next step. So I'm already starting to try to put this into the form that we're used to seeing, which is no coefficient, or 1 times dx dt plus a x of t equals f of t. Right? So I'm trying to get it into that form again. So we'll divide by the coefficient of the capacitor, of the first order differential, to get rid of that. And what that will give us, if you combine all three of these values together, is R1 plus R2 over R1 R2C. So I used common denominators and added them together and then multiplied by the 1 over C. And so that gives us dV dt plus this whole thing times Vt equals 0. And this is similar to the form, again, dx dt plus ax equals 0. So use KCL to describe the system in terms of Vt, and I should probably add something here. Also, what's the right word? Adapt equation to meet the common form, which is that. Okay. So this problem, as you'll see, you'll see that this problem, the f of t is equal to 0. And that means that we don't need to, and we can't split the solution up into two different parts. There is going to be no forced response, okay, because there is no f of t. So we only need to solve the homogeneous equation. So instead of saying x of t equals x sub c plus x sub p, which is previously we called that k1 plus k2 e to the negative t over tau, now there's only one part. And you know what? Maybe to make things simpler, we can call this k2, and I'll say the plus k1 is over here, but it goes away. Because there's no forced response. Okay. Now the problem is now I have to remember to change all these 1s to 2s. 2, 2, 2. Okay. So now, to find the actual solution, we're going to do the exact same thing we did before. We're going to take our solution, we're going to substitute it into the differential equation, and then we're going to try to solve for the values. So if we take this, k2 e to the negative t over tau, we substitute into the differential equation, we end up with the derivative of this plus r1 plus r2 over r1 r2c times the expression equals 0. Right? This right here is here, and this right here is here. So we take the derivative of it. What is the derivative of k2 e to the negative t over tau? It's going to be k2, negative k2 over tau. And then, here, what we're going to do is use the fact that the coefficient of e to the negative t over tau must equal 0 to find tau. All right. So both of these terms are going to have an e to the negative t over tau component to them. So we'll have one coefficient and we'll have two coefficients. And we'll have to add them together. They're both going to have a k2. So I'll pull the k2 out. What we're left with is r1 plus r2 over r1, r2c. That's this one. Minus 1 over tau. So if I cross out the unimportant parts, what you'll see is that this is not going to matter, this is not going to matter, this is not going to matter, because those are all going to be divided out. They're all going to fall away. The part that's going to matter is this piece right here. Because we know that that has got to be equal to this. Has got to be equal to 0. And so when we do that, we see that tau will be equal to 1/5 or equal to 0.2. Okay, so we got one of the values. We don't need to come up. Let me make sure to update all my values here. This is K2, this is K2, this is K2. K2, K2. All right. So we don't care about the value of K2. We care about the coefficient of e to the negative t over tau, which we are going to rename as K3. So, going back to the solution up here, we're not going to try to solve for this value of K2. We're just going to try to figure out what is all of this equal to. What is the coefficient of e to the negative t over tau? And all of this is what we're going to rename as K3. Okay, so, sure. So what we have is K3 e to the negative t over tau is going to be equal to v of t. All right, so we've gotten one of the values. We're still missing the other, which is this newly minted value called K3. How are we going to come up with that? We're going to use the initial condition. Again, just like we did in the other problem, when we need to come up with, that time it was K2. Again, the implementation is a little bit different each time, but the basic steps are the same. So we're going to use our initial condition. We know that K3 times e to the negative t over tau equals the initial condition, because we substituted in for 0 there. Right? Both of these are zeros. And that value we found in the very beginning was equal to 4. And we know what tau is. Tau is given to us. Actually, we don't need it anyway, but and we solve and we end up with K3 is equal to 4. And then we have everything we need. We can state our final solution. So Vt is equal to 4 e to the negative t over 0.2. In the very beginning, yes? Yeah. So I think these two examples go really nicely with one another because they're both very similar type of problem. They use different circuits. One's a little bit more complicated than the other. But it shows how you need to be able to maneuver within the process. You know the process. There's slightly different ways you have to implement it. You have to massage the math a little bit. You have to figure out the way, essentially, to get three variables from three equations, right? When you substitute your solution into your differential equation, you should have something that you can split up into your constant part and your exponential, the coefficient of your exponent. So that'll give you two of the equations. And then the third is going to be using the initial condition. So three values, three equations, and you're going to have to use those to solve. Always in the end, the solution that you should expect to get is V of t or I of t, whatever that value is. And in this problem, I think they actually ask you to solve for I of t. That's easy. It would simply be whatever V of t is divided by R. So we could write it. So I of t will be equal to 4 over R2 exp negative t over 0.2. Ohm's law applies regardless. Has nothing to do with the transient. Okay, so what are the steps in solving this type of problem? One last overview of this before we move on to the next subsection here. We need to solve for the initial condition of our state variable. And the state variable is going to depend on the type of problem that we're trying to solve. Step 2 is to define the first order differential equation in terms of our state. VC if we have an RC circuit, IL if we have an IL circuit. Next, put the equation into this form here. dx dt plus ax equals f of t. We still, in all of our problems, are assuming that f of t is equal to a constant, is equal to a scalar. Like I said, we're not, at least as far as I can see over the next week, we are not going to dive into problems where the external force applied is a time-varying signal. Next step is to note that our solution will take on this form here. And this is all from the stuff that we did last time. We know that our solution will have a particular complementary part, k1 plus k2 e to the negative t over tau. So again, the real problem is not finding the solution. It's finding the attributes or the parameters of the solution. Step number 5, substitute this solution into our differential equation. And then try to solve for k1, k2, and tau using the different equations that we have available to us. So again, like I said, when we substitute our solution into the differential equation, we should be able to split that up into two different pieces. The particular solution will allow us, and this is the scalar or the constant. Part of that will give us k1, and then the coefficients of the e to the something will give us the time constant. Those are two of the values, and then the initial condition, k1 plus k2 e to the 0 equals x0, will give us k2. Now, there's a little bit of wiggle room there depending on how the numbers work out. These two may be flipped, potentially. But that's the general process is, I mean, we've gone over a bunch of times. So, and so the process for this final step, this is what I say here, the process for the final step will depend on the type and form of the system. So doing some homework examples, first going over the examples that we did in class, and then continuing that and supplementing that with homework problems will help. Okay, the next section is the pulse response. It's not that much different from what we've looked at so far. It's essentially applying it 2 times in a row. So I'm going to skip it for right now. We'll come back to it if we have time. I don't think we're going to have time. So that's it for the first section of Chapter 7. Next time, we're not done. Next time, we're going to spend some time going over the quiz. So I want to try to get through a lot of lecture material today, and then next time will be a little bit less because of the quiz. All right, so next topic, it's not really, it's the next logical topic in the progression, which is we talked about first order transient circuits. Now let's talk about second order transient circuits. So these are going to be circuits that have 2 energy storage elements. And you can see some examples here. A parallel RLC circuit, series RLC circuit. And so we're not going to be able to use the exact same solution method as you would expect, because now the form of the solution is going to change, and also the form of the response or the shape of the response could potentially change. All right, so let's take a look at the way these circuits behave. And what we're going to do is use these 2 forms, the parallel and the series, as sort of like the basis for our analysis. We're going to start off by analyzing those 2. We're going to look for similarities between them, and then we'll try to expand it out to the general case, any RLC circuit. So for the time being, let's start off with just those 2. So how would we describe the RLC circuit? This is a single node pair, so it makes sense to use KCL to describe the system behavior. So what we have is 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 equal to IR plus IL plus IC. And that backs up what we see with regard to the labeled currents above. Okay. Then we need to make our usual substitutions. So let's substitute using Ohm's Law, as well as the VI relationships for capacitors and inductors. IR is equal to VC over R. IL is equal to 1 over L integral from 0 to t of VCT dt plus, I'm going to assume the initial condition is 0. Why is everything in terms of VC? Shouldn't this be in terms of VL? Okay, this is a single node pair, so all the voltages are the same. Right? We could call it VC, or like in the previous problem, we could just call it V. And then the current through the capacitor is going to be equal to C dVC dt. And then if we combine them all together, we end up with this form here. And one thing that I did do, like the previous problem, the last example we did, since VC is the same voltage we're going to use over and over again, we'll just call it V. We don't have to call it VC every time. We'll just call it V. Okay, so that's how we would represent the parallel circuit. Let's do the same thing. Let's try to represent the behavior of the series circuit. So for the series RLC, we're going to use KVL, not KCL. And so what we'll see is, if you just look at this right here, VS is equal to VR, is equal to VR plus VL plus VC. And we'll do our substitutions again. VR, this will be using Ohm's Law. VL, L di dt. And then VC, 1 over C, the integral of 0 to t, IC, dt plus, assuming the initial condition is 0. Same thing. Since all the currents are the same as IL, we can go ahead and replace that with just calling it plain old I. So if I were to label that up here, what I would do is I would call this VT, and I would call this, write it like that. All right. And so what we end up with, you can see them both in the screen here, is two second-order differential equations that have a very similar form. If you replace I with x of t and v with x of t, they have the exact same form, right? The only difference, the coefficients are going to be different, obviously, but the forms are exactly the same. And so to make these equations look a little bit nicer, what we can do is, because integrals, they're harder to write. They normally, for these types of differential equations, we tend to differentiate until everything is in terms of derivatives. Just a stylistic thing. So we'll take the derivative of both of the equations, which will make the integral into the equation, and then make the first order derivative into a second order derivative. Anyway, so if you take the derivative of both sides, you end up with two equations that look like this. C, second order derivative of v, plus 1 over r dv dt, plus 1 over L v equals the derivative of is. Then here, L, second derivative of I, plus r di dt, plus 1 over c I equals the derivative of the source. So, why did we do this work above? Because both circuits yield a second order differential equation with constant coefficients, and they have the exact same form, which is shown right here. D, the second order derivative of x with respect to time with a coefficient of 1, plus a1 dx dt plus a2 x of t equals f of t. And so this is going to be the general form that we're going to use for the second order differential equations, just like how we had the other form that we used for the first, as a general form for solving the first order differential equations. Okay, so I think I've put you through enough torture for today, right before Thanksgiving.